In today's class, we'll be looking at some definitions and examples relating them. So, the first definition, we begin with that of an empty set. Empty set is a set containing no element at all. It is also called empty set or null set or void set. Denoted by phi, or we just put curly brackets and inside we do not write anything. This means an empty set. We can denote by phi as well. Let's take an example. X such that x belongs to natural number and x is less than 0. So is there any natural number that is less than 0? No. So this becomes phi. Next definition we have of singleton set. From the definition again we can make out that singleton means there is only one element, a set containing exactly one element. Example, let's take a 1, or we can take example as say A. So A is an alphabet, it's just one element in the set, so it's a singleton set. Next definition is of finite and infinite sets. So an empty set or a non-empty set in which the process of counting of elements surely ends is called a finite set. Or we can basically call a finite set as a set which has finite number of elements in simple language, and a set which is not finite is called an infinite set. Example of finite set: x belongs to x such that x belongs to natural number and x is less than 7. So in this set we'll have 1, 2, 3, 4, 5 and 6. So it is a finite set. Example of infinite set is the set of natural number. or we can take, say, x such that x belongs to real number and x is less than 2 and say greater than 1. So real number, so between 1 and 2 there are infinitely many numbers. That is why this set is also an infinite set. Next definition is of equal sets. A not equals to 5 and B not equals to 5 means we are taking two sets A and B that are non-empty, comma, when n of A is equals to n of B, this condition should hold. N of A means the number of elements in A. We also call this as the cardinal number of A. N of A is basically the number of elements in A. We also call this as the cardinal number of A. And second condition that should match is that first condition is that they should have the same number of elements, and second condition is that all the elements must be exactly same. A is equals to B. Or the elements must be exactly same. For example, say A is defined as x such that x is an integer and x is less than 2 and greater than minus 2. And so this one becomes, this is equals to minus 1, 0, 1. And let's take B as x such that x belongs to integer and x minus 1, x plus 1 is equals to 0. So this is again minus 1, 0 and 1. So therefore A is equals to B. As the number of elements in both are same and also all the elements are same, exactly same, that is why A is equals to B. This is our first example. Let's see example 2. So A is equals to 0 is 0, 1, 2, 2, 2, 3. And B is equals to 0, 1, 3, 2. So A will be equals to B. Now this looks quite absurd, but in sets we do not count repetition. So there is 1, 0, there is a 1, there is 2 and there is 3. So there is 0, there is 1, there is 2, there is 3. Also this arrangement doesn't matter. You can write 1 at the beginning and 0 at the end or anywhere you want. This means the same. So A will be equals to B. The arrangement doesn't matter. Number of repetitions also doesn't matter. Next definition is of equivalent sets. To finite sets, when we talk about equivalent sets, we only talk about finite sets. To finite sets, A and B are said to be equivalent if the number of elements in A is equals to the number of elements in B. Or we can say the cardinal number of A should be equals to the cardinal number of B. example, say A is 0 or 1, 2, B is 9, 7, minus 9, 3. So A will be equivalent to B. A is equivalent to B. So A and B are equivalent sets but not equal. They are equal if and only if all the elements are also same. Here we have n of A is equals to the number of elements in B, that is 3. So A and B are equivalent sets, but they are not equal sets. Okay. Some questions relating the topic. First question. State which of the following sets are finite or infinite. Number 1, x such that x belongs to natural number and x minus 1, x minus 2 is equals to 0. So I am solving them over here only, one by one. So this set is basically, we have in this natural number and x minus 1, x minus 2 equals to 0, means x will be equals to 1 and 2. So therefore finite. Second part, we have x such that x belongs to natural number and x square is equals to 4. So solution. So x square is equals to 4 implies x is equals to plus minus 2. Therefore the set will have only 2 in it because this x is a natural number. So it is finite. Number 3. Number 3, we have x such that x belongs to natural number and 2x minus 1 is equals to 0. So 2x minus 1 is equals to 0 becomes x is equals to half. Now x is a natural number and natural numbers begin with 1. Therefore the set becomes 5. It is an empty set. Empty set is also a finite set because the number of elements here is 1. The number of elements here is 0. There are no elements. In the definition as well, we saw that an empty set or a non-empty set in which the process of counting elements surely ends is called a finite set. So an empty set is also a finite set. Number 4, x such that x belongs to natural number and x is prime. Solution. So we know or the prime numbers are natural numbers and the number of prime numbers is infinite. Therefore, the set is infinite. Since there is no boundation, it can be any natural number and there are infinitely many prime numbers, hence the set is also infinite. Number 5, x such that x belongs to natural number and x is odd. Solution, we have here 1, 3, 5, 7 and this keeps on going till infinity. We have infinitely many odd natural numbers, hence the set is infinite. Next example. Find the pair of equal sets if any and give reasons. So A given to us is 0, singleton set having the element 0. B given to us is x such that x is greater than 15 and x is less than 5. C given to us is x such that x minus 5 is equals to 0. D given as x such that x square is equals to 25 and E is given as x such that x is an integral positive root of the equation x square minus 2x minus 15 is equals to 0. So in the solution, first A is 0. B given to us is x such that x is greater than 15 and x is less than 5. So is there any number that is less than 5 and at the same time it can be greater than 15, which is impossible. So this set is basically empty set. Fine. C, x such that x minus 5 is equals to 0. So x will be 5. D, x such that x square is 25. So x will become plus 5 and minus 5. And E, x such that x is a positive integral root of the equation x square minus 2x minus 15. So we'll solve this. X square minus 2x minus 15 is equals to 0. By middle term breaking, x square minus 5x plus 3x minus 15 is equals to 0. So x minus 5, x plus 3 is equals to 0. We have E as 5 and minus 3. So therefore, none of the sets are equal since they do not have exactly the same elements as the other and with same number of elements. So 5 is here, 5 is over here. They do not have exactly same elements as the other and with the same number of elements, because the number of elements here is 2, here the number of elements here is 1. Therefore, as they do not have the same number of elements, so they are not equal sets. Next question. Number 8. Which of the following pairs of sets are equal? Justify your answer. First one, X, the set of letters in alloy, and Y, the set of letters in loyal. So X will become A, L, O, Y because the repetition doesn't count in a set, and Y becomes L, O, Y, A. As the number of elements in X is equal to the number of elements in Y, and X and Y have exactly same elements, therefore X is equals to Y. The sets are equal. Second, A is equals to n such that n belongs to integer n square is less than equals to 4, and B is equals to x such that x belongs to real number and x square minus 3x plus 2 is equals to 0. So n square less than equals to 4, or n is less than equals to 2 and greater than equals to minus 2, or n so we'll have n as minus 2, minus 1, 0, 1 and 2. Therefore the set A is minus 2, minus 1, 0, 1, 2. Because if you square and check, minus 2 square is 4, n square is less than equals to 4, minus 1 square is 1, 1 square is 1, minus 1 square is 1, 1 is less than equals to 4 is true, 0 square is 0 less than equals to 4 true, 1 square 1 less than equals to 4 true, 2 square 4 which is less than or equal to 4, that is also true. So A contains minus 2, minus 1, 0, 1 and 2. For B now, we'll solve the equation x square minus 3x plus 2 is equals to 0. So this implies x square minus 2x minus x plus 2 is equals to 0. So this implies x minus 2, x minus 1 is equals to 0, which implies either x is equals to 1 or x is equals to 2. Therefore, the set B contains 1 or 2. As the number of elements in A is not equals to the number of elements in B, therefore A is not equals to B. The sets are not equal. Up next, we'll begin with a new topic, sets. So So what is a subset? A set A is said to be a subset of set B if every element of A is also an element of B and is denoted as A subset of B. Let's take an example. See, we have a set A as 1, 2, 3. A very basic example. A set B as 1, 2, 3. 1, 2, 4, 3, 7. So 1, 2, 3. A set A is said to be a subset of B if every element of A, 1, 2 and 3, is also an element of B. So B also contains 1, 2 and 3. Therefore, A is a subset of B. All the elements of A are contained in the set B. Here, B is called a superset of A, denoted by B, a superset of A. Whichever is bigger will keep the mouth open like this, and since A is smaller, here the mouth is closed. Okay. Next definition is of proper subset. So, for proper subset, how we define proper subset is if A is a subset of B and A is not equals to B, then A is called a proper subset of B. Denoted by A is a proper subset of B. We did not mention this equal sign over here. Like here, if A and B were equal also, we could have called A as a subset of B. But here they cannot be equal. For example, let's take A as a 1, 2, 3. B as x such that x belongs to natural number and x is less than 4. So this becomes basically 1, 2 and 3. And C, let's take it as 1, 2, 3, 4. So in this examples, A is equals to B. We can also write this as A is a subset of B because all the elements in A is present in the set B. So we can call A as the subset of B. But in case of C, we write A is a proper subset of C because A is not equals to C. A is a subset of C, 1, 2, 3. 1, 2, 3 is already there. There is also an extra element. Since they are not equal, we can call A as a proper subset of C. We will not mention the equal sign over here. Okay. After proper subset, we have the definition for universal set. But before that, we will just take some notes here. First point, every set is a subset of itself. Because in subsets they can be equal as well. So definitely A is equals to itself, A is equals to A. So we can say A is a subset of A. Second point, the empty set is a subset of every set. Third point, the total number of subsets of a set containing n elements is 2 to the power n. Since the total number of subsets is 2 to the power n, so the number of proper subsets become 2 to the power n minus 1. So this is just a continuation of this point itself. Therefore, the total number of proper subsets of a set containing n elements is 2 to the power n minus 1, because we are removing that set itself. So if we remove the set itself, we'll have one less set. So all of the sets, remaining sets, will become the proper subset. Let's explain this once. Example, say I take a simple set like this, 1, 2 and 3. So subsets are beginning with 5, then singleton sets 1, 2, 3, then we have sets containing 2 elements, 1, 2, 3, 1, 3, and set containing 3 elements, 1, 2, 3. So if you see, the total number of subsets formed here is 1, 2, 3, 4, 5, 6, 7, 8. That is 2 to the power 3. So the number of subsets are 8, that is 2 to the power 3. And if we see the proper subset, number of proper subset formed, we'll just remove this last set, because in proper subsets we do not take the set itself. So the number of proper subsets will become 8 minus 1, that is 7, or we can say 2 cube minus 1. Okay. So the next definition we are going to learn is of universal set. So for universal set, if all given sets are the subset of set U, and then U is known as the universal set. If the superset of all the sets, so universal set becomes the superset of all the sets, because it will contain all other sets in itself. Okay, let's take an example with this this portion that we learned initially. So if we take the set of complex numbers, so the set of complex numbers becomes the superset, because irrational numbers, if we say this is a subset of complex numbers, so all those numbers, whichever set we take, is a subset of the set of complex numbers. Hence, the set of complex numbers becomes the universal set in this case. Let's take another example. Say A has 1, 7, 9. B has 2, 3, 4. Say C has 7, 8, 6. D has 2, 4, 8, 7, 5. So here universal set will become a set which contains all of these elements: 1, 2, 3, 4, 5, 6, 7, 8, 9. Universal set may have more elements than this set also. It is not an issue, but it should at the least have all the elements that is present over here. So U is the universal set for A, B, C and D. Next, universal set is done. So next we'll look at power set. The set of all subsets of a given set A. So power set is a set of all the subsets of a given set A, denoted by P of A. So if the number of elements in A is, say, n or m, then number of elements in the power set of A will become 2 to the power m, for the reason that the total number of subsets of any set containing L elements is 2 to the power n. So if there are m elements, the total number of subsets will be 2 to the power m, and the power set is the set of all the subsets. So the number of elements in this set will become 2 to the power m. Let's take a simple example. Say a set A has the elements A, B and C. So power set of A will have the set phi, the set A, B, C, A comma B, B comma C, A comma C and A comma B comma C. So all of this is present in a set. So power set is a set of all the subsets of the set A. So number of elements in power set of A becomes 1, 2, 3, 4, 5, 6, 7 and 8. That is 2 to the power 3, which is 8. Since the number of elements in the set A is 3. And the last topic, intervals of subsets of the set of real numbers, or intervals as subsets of the set of real numbers. Okay. Initially we'll take two numbers A comma B belonging to real number and A, B less than B. So first type of interval that we see is A comma B. We are putting this under square brackets. So this denotes x as a real number such that x is less than equals to B and greater than equals to A. So this closed bracket denotes that A and B are included. This is also called as closed interval. The set A comma B with first brackets is x belongs to real number such that x is less than B and greater than A. This is the set of open interval where A and B are excluded. Third is A comma B. Say in B we are putting closed bracket. Okay. One more thing, this open bracket can also be denoted as like this. We are writing A and we are putting this bracket in the opposite direction, square bracket in the opposite direction. This means that A is excluded. So this is basically x belongs to a real number such that x is greater than A and is less than or equals to B. Means B is included but A is excluded. So we call this as left half open interval. And number 4, say A is included, B is excluded, or A is included, comma B is excluded. This becomes x belongs to a real number such that x is greater than or equals to A and less than B. So this is called a right half open interval. So the length of the interval in all of this case is B minus A. The bigger number minus the smaller number. Be it open, be it closed, be it half open, it does not matter. We take the length of interval as B minus A, where B is the larger number and A is the smaller one. Okay. We'll look again at some examples. Example 9. Consider the sets phi A is equals to 1, 3, B is equals to 1, 5, 9, C is equals to 1, 3, 5, 7, 9. Insert the symbol is a subset or is not a subset between each of the following pairs of set. So solution. So phi is a subset of all the set. So phi is a subset of A, phi is a subset of B, phi is a subset of C. Now we have say A. A is not a subset of phi, A is not a subset of B, but C has 1 and 3, so A will become a subset of C. So A is not a subset of phi, A is not a subset of B, because A contains 1 and 3, but B contains 1, 5 and 9. So since 3 is not here, so A will not become a subset of B. But A is a subset of C. Now B is not a subset of 5. B is not a subset of A, but B is a subset of C, as 1, 5 and 9 is contained in C. And C is not a subset of 5, C is not a subset of A, and C is also not a subset of B. Since the elements in C are not present, all the elements of C are not present either in 5, A or B. 5 does not have any element, so we do not even consider that. Next example 10. Let A be a set having A, E, I, O, U and B is a set containing A, B, C, D. Is A a subset of B? Or is B a subset of A? Why? In solution, A is not a subset of B because the element E belongs to A, but E does not belong to B. Because a subset, if A would have been a subset of B, then B should have all the elements that is there in A. And there is an element E which belongs to A but does not belong to B. Hence, A is not a subset of B. And B is not a subset of A because B, small b belongs to capital B, but small b does not belong to A. Therefore, B is not a subset of A. All the elements of B are not present in the set A. And the last example, example 11. Let A, B and C be three sets if A belongs to B and B is a subset of C. Is it true that A is a subset of C? If not, give an example. Solution. So let's take something. So A, B, C and sets. So A, let's say a singleton set having the element 5. So A is present in B. So the set B, while defining, this has the set 5 in it. This A is there present in B. A belongs to B. So this, the root set of 5, singleton set 5 is an element of B. Say it has other elements like say 2, 3 and 4. Now B is a subset of C. So C is a superset. So it should have all the elements that is there in B. And it should have some more elements as well. Say this one. So therefore A belongs to B and B is also a subset of C. So the question is satisfied. Now we need to see if A is a subset of C. A has the element 5. See, we do not take 5 here. If we take 5 here, then it becomes a problem. So it is not important that 5 should be here. So 2, 3, 4 and 6 is here. See. So A belongs to B. A is belonging in B and B is a subset of C. So is it true that A is a subset of C? So this, the set 5 is not a subset of this one. because this A belongs to C. This set is present in C. But when we have to take a subset of C, it will become set containing the set 5 is a subset of C, and A is not a subset of C. Please understand this clearly, that the set containing 5 is an element of C. When we take a subset of C, it will become the set containing the set 5. This becomes a subset, and this is not A. Hence, A is not a subset of C.